Hi, I'm Francesca Campoy, and this is Just for Funk. Welcome to episode number 38 of Just for Funk and number 2 of Machine Learning for Gophers. Today we're going to be continuing what we did on the episode number 1 of Machine Learning for Gophers, which was episode number 34 of Just for Funk, which will be linked here or somewhere here up there in one of those corners. By the way, if you have not watched that video, I recommend watching it because we're going to be adapting the code that was there. So if you don't understand the previous code, it's going to be kind of hard to get what I'm doing today. So yeah, go watch it if you have not yet. I'll be here waiting for you. If you have watched it already, you might remember that what we did was generate these graphs. And this graph here specifically shows a bunch of different points. And then what we did was add one line. That line is supposed to approximate those points. That's what we call linear regression, which I will mispronounce basically every single time I try to say it. But once you do linear regression, what you do is you basically find the line that gets the closest to all of the points. Or rather, it minimizes the distance between the line and all of the points that you have. That's linear regression. There's a couple ways of doing this, and the one we're going to be doing today is actually applying what we call gradient descent. So basically, rather than just trying to find a solution directly, we're going to try to see how bad or well we're doing, and then decide to take a next step into some direction given some information. That's not so fun? Let's get started. Okay, so I started actually by copying the code from episode 34 into a new directory. So this one is the one I call 38 linreg vanilla, because we'll be doing linear regression without using any framework other than GoNum for plotting, but we'll not be using neither TensorFlow or Gorgonia, and actually not even GoNum for linear regression or anything. We'll write it by ourselves to get that first piece very well understood. There's no better way than understanding something than writing the code that does it, really. So let's get started. Let's see what code we had. Okay, so let's open that code and see what we have in there. So we are reading this data.txt, and data.txt has a bunch of points. So every single line is x, y. And then once we have that open, we do plot data, and plotting data creates a file, creates a new plot, adds the scatter, and that scatter basically is every single one of the points will appear as a different point in the graph. And then we create a line, and the equation of that line is this one. Why? Because why not? Because it looks pretty good, right? So what we're going to do is actually replacing this with linear regression of XYS. So we're gonna try to find the line that matches, that gets the closest to all of the points as shown in here. But maybe this one was not the best. Maybe we can do something better. So we're gonna do that with a program. Cool, so let's write that. So we get our plotter.xy's, and then we return two values, m and c, which are float 64s. Okay, why do we return two values? Well, because any line can be represented, any line in 2 dimensions can be represented by one value for x. So what value you multiply x with. So what value you multiply x with. So something like x times m plus c. With that, you can represent any line. So that's what we're going to be doing today. Rather than returning some extra fancy thing, we just return those two values, m and c. Cool, so they're already defined because we're using them as return values. So I don't need to do anything to them. I can just return them at the end. Technically, you could just do return without M and C. We call that a naked return. And I don't like them because the problem is when you do MC, all of a sudden you are kind of doing it implicit return. Makes it a little bit hard to remember what you were returning. So, explicit is better than implicit. So return M and C. Okay, so what are we going to do in here? Well, So we could choose some random value, right? Like we have this. So let's just do that. M and C and just return that. And so if we run this program, go run main.go, out.png will have no change because it's exactly the same thing, right? But now the interesting thing is this the best we can do? Well, before we answer that, we should first answer the question, what is good in this context, right? Like, what is that the thing that we're looking for? So if you cannot measure, how are you going to improve? So let's measure how good this is. And actually, there's a nice way to measure it, which is measuring the distance in between for every single point, the point you predicted and the point you actually got, right? So basically, for every single one of these lines, you're gonna go and say, whoops, there you go. From the point I predicted for this one will fall on the line right here, but there's this distance here, and that is the error distance. So what we're going to do is just add all of those differences together. But since those distances could be positive or negative, and then if you had basically the equal distance, like all of the distance were equally bad in both directions, then we have be 0. So instead, we're going to multiply those values by themselves, because when you square something, you get something positive all the time. That way we have a positive value, so the minimum will always be 0, and then we'll divide it by the number of points we have, just to have a better idea of how far we are, no matter how many points we got. Okay, so how do you write that? Well, that's actually what we call the cost function. So I'm gonna call it cost for xys. So plotter.xys. But also I need the line that we're approximating, right? Because we are computing the cost for a line approximating a scatter of points. So MC float 64, and that will return a float 64. The cost is a single value. It's scalar, not a vector. Cool. So how do we do that? Well, what I said is that the cost is so 1 divided over the number of points times the sum of the value we actually got minus the value we predict, which is m times x plus c. And then we're going to, for every single one of those, we're going to do square. That is the math version. Now let's translate that into Go. So that would be C, I'm going to say 0 and return C at the end. Let's call it S because it's like sum too. And then for every xy point in our xys, we are going to do d is the difference or the distance if you want to, and that is xy.y minus xy.x times m plus c. So that is this part here. And then we're going to do s plus d square. So that we're doing the d square like this, and then the sum. And then we need to remember to actually multiply that by n, 1 over n. So yeah, 1 over n. Yeah, I don't know why I always say that wrong. So that's the same as dividing this by n, which is the length of xys. Cool. So this is the cost. Cool. So why do we like this, right? Well, because it actually shows us how good we're doing. So let's try it out. So let's print cost of 2.f. I'm gonna copy that because okay. So cost of MC is cost of M, XYS, M, and C. Cool. So let's run the program again. Okay, so this says 9.86. Cool. Is that good? Well, let's see. What if we do 0.0? So 0 on both sides. So the value is much higher now, which is interesting. And can we see the difference? So let's see if I'm able to zoom out. There you go. So yeah, we can see the difference. This line doesn't really approximate at all, right? So if we do Let's try m being 1, which means that it will go straight up, if I remember correctly. Now this is a little bit better, and we can see that the cost goes down. So the cost basically represents how well we're doing. A cost of 0 would mean that we are able to match every single point, which is impossible because then it would not be aligned because all of the points are not aligned, right? So 0 is the minimum, although it's impossible in most of the cases unless all of the points are aligned perfectly on one single straight line. That's not the case in this case. So what we're gonna try to do is try to find the point with the lowest cost. How could we do that? Well, let's go the easy way, for loop, right? So let's say that since we have two values, what I can do is I'm gonna call it, actually, let's try to use these things. They're always cool. So for count is going to be, so I'm gonna call it min and max, and then have the same thing inside, but for C, so IC, and this is going to be plus equals delta and plus IC plus equals delta. Okay, so why am I doing this? Because what I'm going to do here now is keep track of the mean cost, which to start with needs to be as high as possible. So I'm gonna choose max float 64 math.max float 64, which is just a very, very large number. It's the largest number you can represent with float 64s. And then here I'm going to do C equals cost of XYS IM IC. And if C is less than mean cost, then we're going to set mean cost to C, and then C and M and C to, sorry, I'm mixing things. Let's call this cost. Okay, so let's call this compute cost. Otherwise, it's gonna be a pain. So cost, and IC. Cool. C is so C in here. It's called C because it's the constant that you add. It doesn't multiply by anything. It multiplies by 1. That's why it's C. But I don't want to use C and cost at the same time. Okay, so we need to define those constants. So let's say that the minimum is going to be minus 100. The maximum is going to be 100, and the delta is going to be 0.1. Cool. So, okay, so now what we're doing is we know how good things are, how good solutions are, right? So we're gonna go point by point trying to figure out on that space defined by M and C, which point is the best one. And if we do that, it should return something, but let me let me print what we got actually, because otherwise it's not that useful. Okay, so compute cost of that. Okay, so we got 8.96, which is actually better than last time. Last time was 9.86. So instead of 1.2 and 3, we do 1.2 and minus 4. Apparently that's a better solution. And if we look at the image, it kind of looks the same, but it's a little bit better apparently, right? At some point, the results are so similar that at naked eye, it's very hard to tell. That's why we need a specific number that tells us how good this is, and that's cost. Cool. So now we're able to, given the cost, just explore the whole space of possibilities and find what's the best result. Now, there's a couple problems here, right? One of them is the fact that I had to define min and max, right? What happens if the best result is actually outside of this area? Well, you will not see it. So probably you want to do something like math.mean float 64 to math.max float 64. And then, actually, that's not even a thing, because that, of course, is not a thing, because that's not how floats work. But whatever, you go from from the minimum float 64 to the maximum float 64 to make sure that you don't miss any values, right? Sure, that's gonna take a long time. And even worse, what happens if its delta is too large? Because you could say it's 100, right? But then you're gonna miss the right result. So you wanna maybe do 0.1, or maybe the 0.01 or 0.01. Now, if you run this program as is right now, it will take forever. That's a problem. So rather than doing a blind search over the result space, we're actually going to use gradient descent to figure out where to go, right? And this sounds like it might be magic, but it's actually pretty straightforward. What we're gonna do is we're going to use derivates. So what are derivates? Basically, it tells you what is the steepness, how steepness is a word? Steepness. I'm gonna say steepness is a word. So how steep something is, right? So 0 means it's completely flat, positive means that it's going up, negative, it's going down. So that is something quite straightforward, and it works in one dimension. If you have two dimensions, then you have two numbers, one telling you if it's going up towards the north, the other one up towards the east, right? With that, you basically define the whole thing. Well, turns out that that's exactly what we're going to do here. And we can find that value by using derivates over the cost function. Once we have that, what we're going to get is basically the direction on which the cost goes up. So if we follow that, we'll go to the highest cost possible, which, you know, that's not a great idea. But if you go the other way around, you're going down to the lowest point possible. So that's what we want to do. We want to see in what direction the cost moves up or down and follow the direction that goes down. So let's try to do that. So basically what we need to do is get this function here and do some derivates. Might seem like this hard maths. It's not that hard. If you don't get it, I will link to a blog post that might be helpful to you. Also, there's a Coursera course on this, and there's a bunch of videos. I will link a video from here just to make sure that you can watch it if you want to. But I'm gonna go through it pretty fast in a very straightforward way. So instead of compute cost, we're gonna need to do compute gradient. And the gradient, it will be returning derivative of m, derivative of c, which are both float 64s. For the rest is exactly the same, right? So basically it's given these points and these values m and c, find in what ways we can, if we go up with m or up with c, how will cost change? So the cost by dm. This is not technically accurate representation, mathematical representation or notation or anything like that, but this is basically the cost, how the cost changes as we change m, right? So that will be 1m stays the same, the sum stays the same. This part here though, since it has m, this outro will change, and this basically x squared, so that will become 2 times whatever there was inside of the quadratic expression, and then the derivative of this thing according against m, which will be, this is a constant, this is a constant, this is not a constant, this is x. So it'll be x, and we can make that look a little bit better, and that will be by moving the 2 here. And then the x, we can move it, oh, actually minus x, sorry. Minus x, because there's minus right there. So that would be minus x times that. Cool, so that is one way to represent it. And then, actually, let's copy that and make that also dc. So dc, all of this will stay exactly the same. The only difference is that here we are derivating according to c, not m. So instead of minus x, we'll get minus 1. So at the end, we get something that is extremely similar, except for the fact that there is a minus 1. So you can write this like this. Cool. and let's drop the old ones. And you can write like this if you want to. I think this is better. Cool. So now let's compute those with Go. So dm and dc are already computed. So what I'm going to do is simply iterate over all of the x, y, s and compute the common part. This is common to these things, but also common to this one. We call that d, the distance. So we're gonna need to compute d for sure, and then dm will increase by minus x y times x times d. So that is this part here. And dc will increase by minus d, simply. Cool. And then we're going to return. So we need to compute this 2n. So I'm going to call that, I'm going to do just n, which is float 64 of the length of x, y, s. And we're going to use 2 divided by n times dm and 2 divided by n times dc. And that is not correct. Oh, because that is range, not 4. Okay, cool. So with this now, what we have is we have something that not only it tells us how well we're doing, right? But it tells us in what direction we should go to do better. Technically, it tells you in what direction you should go to do worse, but basically you just go the direction opposite and you're good. So let's try that, right? So let's move this to what we had before, because otherwise it's kind of hard to compute anything valuable. And what we're going to do is, on top of printing the cost, every single time we find a better solution, we're also going to print the gradient, compute gradient. So compute gradient, and that's going to be the gradient. Okay, so let's run it. And compute gradient now returns 2 values. So we need to do dm dc equals this, dm dc, and that's going to be something like this too. Okay, so now we get a bunch of values, but what do they mean? What do those grad mean? Well, what this means is that, for instance, if we block 1.20, we're blocking m, which is going to look at c. What this value says of 4.20 is that when you are in 420 for C, this number here, it tells you that if you go lower in C, if you decrease C, you will increase the cost, right? Which is not what you want to do. So what you need to do is you need to increase C to decrease the cost. And that's why we go from minus 420 to minus 4, right? So that makes sense. We're moving forward to reduce the cost. And if we have any other, which is minus 4, let's see, minus 4 anywhere around here. Did I miss it? Nope, there's no minus 4 there. There's no minus. Okay, cool. So minus 4, 0.10. So this says that from 0.10, you should. So if you decrease m, you will increase the cost. Therefore, you want to increase m to decrease the cost. So the good m should be over 0.10. And the best then is 1.20, so which is way higher, right? So that's the point of the gradient, the fact that it points you towards the right direction. So then instead of doing all of this iteration, which can be quite expensive, what we're going to do is simply iterate a given number of times. So let's say we iterate 1,000 times, and we'll talk about how many you should be iterating later. We're going to compute the gradient at the current point where we are, MC, and we're going to be using that to move in that direction. So rather to move in the opposite direction. So the M will be increased by, M will be moved in the opposite direction of the M, and C will be moved in the opposite direction of DC. Why am I using plus, equals, minus? Because I want to make sure that it's very clear that we're moving the opposite direction of the gradient. That's really important. Otherwise, you just move forward towards infinite and you get not a number everywhere. Okay, so let's see what happens if we run this. And I don't want to print that necessarily, so let's try this. Could not plot data, none. Okay, so that's not good. As I told you, that's a risk. You can get no numbers quite easily. Let's see from the beginning what's happening. Okay, so we start with a very high number, and the number keeps on going higher and higher. But we're moving towards the direction that we said was the good one, right? So what's going on? Well, imagine that you have that valley, right? And you are here. And then I tell you that the lowest direction is somewhere towards this direction. So the lowest is here. And then instead of moving a little bit, you just move a lot. So you end up on the other side of the mountain, but not at the same height or below, but actually even higher. So now when I tell you the direction is the other way, I'm actually going to give you an even larger value. So you're going to jump even larger. And basically what you're doing is you just go outside of the valley all completely. That is divergence. That's not what you want to do. What is the solution? Well, actually to take smaller steps, as simple as it sounds. And that take smaller steps is the normal way of saying this thing that it's called the learning rate. And a learning rate is something that you pass to linear regression. So normally you got it alpha, and it's float 64. And what you're going to do is simply multiply alpha times that. So let's do it times alpha and times alpha. And this seems like a silly thing, but this is totally what you're going to be doing with linear regression. So if you do 0.1, let's try to run the program again. We're still not going there. We're exploding. Let's see now. 0.01. Now it seems like this is going lower, and now it's actually working. How do you choose alpha? Well, you choose an alpha that allows you to see the cost go down. That's it. There's many techniques, but basically you need to find one that does that. So let's remove the less. And now we see that the best result we've seen so far is actually 1.8 and 3.79. Is this better than the one before? Actually, I think it's around the same. But maybe we can do more steps and simply do, instead of 1,000 steps, let's do 10,000. So let's see, 8.95. So that's even better, right? And if we do even more, let's see. Can we get, no, we don't get lower than 8.95. Cool. So with this now, the thing is that we're able to see that this is the best line we can draw to approximate the results. And that's kind of hard to see right now, but I came up with this idea, which is instead of iterating all of the times right away, what I'm going to do is I'm going to make this a parameter of the program. I'm going to call that iterations. And I'm going to make that a flag. This is not necessarily iterations, which is going to be an integer. This is not necessarily the best solution, but I think this will help you understand how the algorithm works. So let's make sure we do flag.parse and flag.int var of iterations. I'm going to call it n. The default value is going to be 1,000, number of iterations. Cool. So now if I do go run dash and 100, you'll see that this moves a little bit. And now if I'm able to write a for loop in bash, which is one of the hardest things of the whole episode, we should be able to do for n in sequence 0 to 100, do go run main.go dash and n and sleep 1 second and done. Okay, and now you can see how that line is going to be changing over time, little by little. And it's going to be showing you a better solution every single time. And you can see how the cost is actually going down too. Slowly, but surely. And this is what that gradient descent is. The gradient descent is basically using the information of the derivation of the cost function in order to move towards the solution step by step, doing it little by little. And that's it. So linear regression can definitely use gradient descent, but basically every single machine learning algorithm is based on this specific thing, which is just using the derivative to go towards a solution. Neural networks use this too. Everything I know basically about machine learning at some point uses gradient descent. So I think it's a great important thing to know really how it works. So that's pretty much it for today. I hope you liked the episode. It was hard to record. I had to record it twice because I messed up with the mic in the first time and ended up with a video with no sound, which is not cool. But anyway, everything for you people. Also, this is the second episode of Machine Learning for Gophers. More episodes are coming because I will be trying to implement the same thing using TensorFlow for Go and also Gorgonia. If you have any ideas about other episodes you'd like to see, if you have your code reviewed, which by the way, I'm still waiting for more people to send code reviews. I have some of them that are kind of prepared, but they're not great. They're not exactly what I want. So if you have some code that is not too hard, not too simple, send it my way. I'll try to see if we can make an episode out of that. As always, thanks for watching and see y'all in 2 weeks.